Hello students, and welcome to this module about district heating, district cooling and electricity production. This is the first technical module, and we will discuss briefly the potential and ongoing development. And I will give you some key equations and values for use later. So you will learn a little bit of how to think in the planning stage and how to get a first idea of whether or not a district energy system might be feasible. So the learning outcomes from this module will be that you know some basic terminology and you have a few tools to estimate if district energy is feasible or not in a specific location. I will want to refer you to the roadmap report from IRENA that you downloaded previously. I'm well aware that the report is from 2017, but the background and the fundamentals are still valid. So you should start by reading the executive summary. It's only 8 pages. So pause the recording now and read those pages. So, welcome back. Is your country one of those mentioned in the report? Even if it's not, I hope you now have a first insight to district energy. And based on the fact that, as an order of magnitude, 1/3 of the global energy use is for space heating and cooling and for tap water heating, you will appreciate that there is a huge potential to expand the use of district energy. The pie diagram on page 3, though, is a bit alarming. In 2014 was about 90% of the district energy supplied through fossil fuels. But district energy is a low-temperature service, so there is really no thermodynamic need of high-quality primary energy. That is the basis for the reasoning presented in the summary, ranging from page 5 through 8. Does your region have any plans for renewable district energy? Let's talk a little bit about what affects the local potential for district energy. The examination task for this lesson will be for you to do a local feasibility assessment, and then you will use the methods outlined in this module. The linear heat load, or the linear heat density, is a crucial measure. As a very rough rule of thumb, you'd like to stay above 5, 6, 7 something gigajoules per meter. The higher the better. The threshold value depends on several factors, so it is not written in stone. But if it is below 5 gigajoules per year and meter, you know you are below a realistic limit. Often 7 gigajoules per meter is assumed as a realistic level. It is obvious that the total income to the heat provider is a direct function of the amount of energy sold. And it is relatively simple to accept that the capital cost for the distribution network will be a direct function of the length. And it is also a trivial thing that the loss of heat from the system is a direct function of the total length. But then these numbers are not known before the system is built. So in this slide is an alternative setting of this equation. The way you choose to estimate the linear load must be up to your specific situation and to the data that you can find. But then maybe you cannot find these data either. And in that case, you will have to set up some other way for your estimate. Maybe can general data on population density and area heat need be used. For Europe, there is a thermal atlas available, where you can find the heat needs subdivided to square kilometers. Maybe there is something similar for your region. Basically, you will have to do similar estimate for the cooling needs. Then you will have to have an idea of your potential customers. There are significant differences between customers. Some, like individual households and schools, will have pronounced daily variations. Some, like hospitals or factories with 24-hour operation, will not. Some, like greenhouses or outdoor pools, will exhibit huge variations over the year. Plotting the momentary demands as a function of linear time will result in what we call a load diagram. This will help in planning since it will give you an idea of the momentary loads. The philosophy behind district energy is to supply a large number of customers. It goes without saying that what I'm talking about now are individual random peaks, like the peak demand during mornings when individuals have their wake-up morning shower. These things will be clear from the load diagram. Though many customers may have a common overall behavior, will simple statistics show that the total peak load demanded will be less than the sum of the individual peak loads. And this is documented as a simultaneity factor. Again, is this something that must be determined empirically? Maybe can you find an approximate value available from some comparable region nearby? If no data are available, you will have to rely upon a simplified equation. This equation can be used to group customers into larger aggregates. And if these aggregates are selected so as to become comparable, then can the aggregates again be combined using the same equation once more. Typically, is the demand for hot water in the kitchen and or bathroom short but intense. So the ratio between mean and peak values will be very small, and the smaller this ratio, the more pronounced is the reduction obtained via the simultaneity factor. It is obvious that this is a very approximate method, but then if you have nothing else, you have to do something. That was for the random variations, but now let's spend a few words about systematic peak loads. Climate will cause seasonal variations, which are obviously the same to all customers. There will also be daily variations. These things hit all the customers the same way, and there is basically no random effect at all. So for these, there will be no reduction factor. The high load case for the system is simply the sum of the high loads for all customers. What you want to do is to set up a duration diagram to characterize your selected area. In the duration diagram, you use the vertical axis to illustrate the total power, watts, demanded for heating or for cooling. And on the horizontal axis you indicate time. But the time is not clock time of the day or dates or so, but it's accumulated time. So it's not linear any longer. So if we assume that this diagram would be for a location in Sweden and would represent one full year, then we would find the months January, February and December all in the high load end in the far left. And then would May, June, July and August all be at the low load end at the far right. And the remaining months would be in the middle. So it's not calendar time on the horizontal axis, it's accumulated time. To estimate the power needed, you will have to estimate or collect some data about the buildings. To do that, you want to find some type of energy demand measure. So what you want to find is a relevant energy signature. The energy signature is a graph that connects the heating or cooling power demand with the outdoor temperature. In most cases will these data be nearby linear. There will be a set of 0 or near 0 cases when you need no heating at all or no cooling at all. And then there will be one limiting temperature below which you have to provide heating to maintain the proper indoor climate. And there will be another limiting temperature above which you have to provide cooling. If you find no statistics or are in the planning stage, so there are no buildings yet, then you may want to refer to the rules and regulations for new houses valid in your country. For the energy signature, you would want to use degree days as the measure of outdoor temperature. If you're not familiar with the concept of degree days, then I would recommend you read the introduction at degreedays.net. That introduction will tell you everything you need to know about what degree days are and how to use them. Any degree days data you will need to solve the task by the end of this lesson are available at this site, degreedays.net. Since data can be aggregated for days, weeks or months, it will also be simple to aggregate the degree days so as to match the bills from the energy company. Thus you can set up the energy signature for an existing building, only provided you can see the energy bills. Only if, in the future, you need access to more advanced tools for analysis will you have to pay for it. We will not spend much time on economy, but a few things need to be mentioned. First, it must be appreciated that if you are starting from nil, then the investment costs will seem overwhelming. But then you have to remember two things. District energy is long-term. For the production unit, you can use maybe 30 years depreciation time. And for the distribution, it may be set at 50 years or longer. Second, you must consider how you want to start. It is quite possible to build a system step by step. So you build a small local network first and make that run. And then you build a new one. And after some years, you start connecting the small networks to each other. And then, maybe, the system is large enough to accommodate not only heat production, but also electricity and cooling production. Or, of course, the other way around. Not only cooling production, but also heat and electricity production. Generally speaking, and simplified, may we say that the investment cost for the distribution network is linear with pipe diameter and linear with total length. It is also obvious that the heat losses and the pumping costs will both be strong functions of pipe diameter and total length of the system. So the mapping and design of the net is of paramount importance for the overall economy. Then just one more thing. Do you remember the duration diagram? There were 3 loads indicated: high load, low load and intermediate load. Now assume 3 different production units and further assume that the duration diagram is valid for a full year. So we have a winter load, high load. Summer load is the low end, and then spring and fall are in between. And then we have 3 different production units. The production costs are composed of a capital cost, which is constant, and a total operational cost, which is constant as per power unit produced. So we multiply the specific cost with the power produced to get the operational cost. The lower diagram now shows the total production cost for each of the 3 units. And as you will see, is the blue curve for unit 3 the one with the lowest total cost for smaller amounts of energy. Do not mix this up now. The amount of energy may be small from unit 3, but the power delivered is high. So this is the cheapest one to use for high load. The green curve for unit 2 is the optimal for use during spring and fall. And unit 1 is the best one for summer load. Again, is the amount of energy delivered small, but for summer load is also the power demand low. Now, the capital cost and the operational cost will reflect different complexity in the plant hardware itself and different fuel costs. To have a low operational cost, you will have to have a very cheap fuel. A cheap fuel is unspecified and has a very variable quality. Such a fuel will demand a very advanced unit, so the capital cost will become high. For the capital cost to become low, you need a fuel that is simple to handle. So that is a very qualified fuel, a high qualitative fuel, an expensive fuel. So then you will run into a high operational cost. So for different load cases, you will want to use different fuels in different units that are adapted to these fuels. And that is what I want to illustrate in a very, very qualitative way in this slide. And that ends the presentation of this module.